So you can watch back the video later. I won't do it because I hate hearing myself back, but for those of you interested in passing on some of these slides, I'll put on the slides online later as well. Okay, we're still okay for audio?
Yeah, we are.
Good. Okay, let's get started. I need to move some of these fields now. Okay. Okay, so do you see the slides?
Yes. Yes.
Good. Okay, so thank you, Mika, for organizing this, and most of all for getting up early this morning and trying this out with me when I was in the hotel. So I'm in Sweden at the moment, giving a sort of whirlwind tour of new features of the 2014 release, and at the same time now trying to give an update for the people at the Southern Hemisphere. So as I mentioned, if you have any questions, just drop me a line via the chat function, or you guys at the ANU. You can just, I can hear you over the audio, so if you do have any questions, just drop them. Okay, so let me see. So this is what I've planned for today. So I first want to start with a bit of background and history of where we come from, so where Amsterdam Density Functional has started, to the people who founded ADF, and then that evolved into the company that we are now, Scientific Computing and Modeling. Then I want to spend most of my time talking about Amsterdam Density Functional, which is still our flagship program, if you will, and I'll focus a little bit on giving some examples of spectroscopic properties, for which ADF is quite a good code. There's a few slides specifically on organic electronics, solvation and environment effects, and I'll talk a little bit about bonding analysis. It will take about 30 slides or so, and then we can zoom through things if it's problems. So sorry, I have to answer to somebody who has problems with the sound because obviously they can't hear me. So I just have to click in something. Just give me a sec. Sorry about this, so I'm easily distracted, as you see. So after I talk about Amsterdam Density Functional, then I'll move on to our periodic DFT code, and I'll spend a bit of time on density functional-based type binding, so explain what that is later on. It's basically a fast way of doing DFT, more approximate, but much more faster. And then go on to ReaxFF, reactive molecular dynamics, and if there's interest, then I can say a little bit about COSMO-Rs for doing properties of molecules in solution, basically. Take a look at it real good.
We are interested in COSMO.
Sorry, Rika, could you say again?
We are interested in the COSMO.
I didn't quite catch that. Rika?
Yeah. We have interest in COSMO.
Sorry, Rika, I still can't hear you. Let me turn the volume.
Yeah.
Okay, so is the audio having problems again? Can you hear me? Do people nod in the back if you can hear me? Yeah? Okay, that's good. Okay, then, I'm sorry, I didn't quite catch your question. So, if it's very urgent, type it into the message box. So Rika will afterwards be those people sitting there in the background nodding, give a hands-on workshop. So I'll leave that into her expert hands. Moving on then to a bit of background of where we come from. So, so this is the obligatory slide on multi-scale modeling. ADF, that's where we come from, strong for molecules, the systems up to say a few hundred atoms, and slowly moving into methods for treating larger systems for longer time scales. So, semi-empirical methods, still quantum mechanic based, and then there's atomistic potential methods, as well as kinetic Monte Carlo methods for treating large systems for longer time scales. So these people, John Barnes from Ziegler, they're very well recognized chemists, both in the theoretical world as well as in the experimental world. They were both together in Amsterdam in the early 70s, and they started then writing a code called Amsterdam Molecule, AMOL. And at that time, it was one of the only, if not the only, density functional code written specifically for doing chemistry. So DFT was frowned upon within the chemistry world, but it was pretty mainstream at that time already in the physics world, because it was the only way that you can treat, in an ab initio type of way, solid-state systems. So 20 years down the line, that resulted into the code that we know now as ADF, and a small company was started, Scientific Computing and Modeling, SCM, that basically gave support. So the business model at that time was giving support to academic user groups in Japan that recognized the strength of ADF, specifically in inorganic chemistry, precision metal chemistry. 20 years further down the line, so 2014 now, we have 12 people that are hired by SCM, 8 of which have done their PhD either in chemistry, theoretical chemistry, computational physics. And on top of that, we have a few pension people, if you will, so those are PhD students or postdocs that are hired from money we get from the EU for participating in networks. So that's making new technology available. And from our side, of course, is the software development. From those two people, of course, all their PhD students and postdocs that have learned to write code in ADF, some of which are still actively developing ADF, and so now we still have many academic collaborations going on worldwide. So nice synergy, because with those academic groups, they can give new functionality to us, and then we can do all the boring stuff that goes into making the software commercial. Namely, it needs to be tested, it needs to be documented, debugged, optimized, ported, and so on. All the kind of things that you can't really write a paper on when you're in academia. So we do all the boring stuff, and the academic groups, they do all the new development. Sorry about the noise in the background. I'm setting up the conference here at the same time. Okay, so as I mentioned, all these academic groups that contributed to ADF and all the codes that I'll talk about later on. So currently we have about almost 90 people that have significantly contributed to what our software is today. So we're quite we acknowledge, of course, their contribution. We're quite obliged to them to have the software is what it is today. Just to give you a few faces, so this is on the top. These are our core developers, if you will. So those are the people that have been longest with ADF. They each have their own speciality. And at the bottom here, these are the younger dogs who have more recently joined SCM, and they can take on some of the more technical issues that go into software development. So we have a PhD student, Mirko Fantini, who's a very brilliant scientist, but he's doing very technical stuff that would be very hard to get a PhD project funded on, but it's very useful in terms of getting our software more accurate and more robust. People doing the business side, that's of course also necessary. So That's Frida. That's the person you deal with when you have any problems with your licenses. Very efficient, very good. That's Tom, who runs the show, and then there's us two guys, so that's me, and that's Sergio, that do sort of, these kinds of presentations, going to conferences, talking to groups that want to collaborate, and specifically we're talking a lot about the EU project. There's also Kitty, who's now running the office since Frida at the moment is in Australia, enjoying a well-deserved time off. She now will be doing a lot more of the licenses at the moment. So if you have any fire requests at the moment, then probably Kitty will take care of that. We have a few EU projects. One just finished today with Jakobs University in Bremen, and so that's Thomas Heine, and we also collaborate with him on two different projects. So one that's more or less halfway, it's called Propagate, where Michiel and Robert are specifically looking at Applicio molecular dynamics, both in the ground state using von Oppenheimer, or in the excited state using Liouville and Neumann dynamics. And one student, Michal, specifically looking at developing QMMM, so further developing QMMM treatment. There's another project called MOSES, and that has nothing to do with splitting water, but it has to do with two-dimensional semiconductor materials that are made of molybdenum, sulfur, or its heavier congeners, tantalum and selenium. It's a big, that's a big IPN, so innovative training network, where we collaborate with a few universities as well as small companies, also companies making these types of materials. And there we're working on charge and heat transport properties as well as two-dimensional excitations or optical properties. And we'll soon hire a postdoc for that specific purpose. Moving on then to a bit more science, so I want to give you an overview of what ADF is capable of. Obviously, it's sort of limited to a selection of slides that I've picked. I see people in Brisbane having problems, so just let me type in a few lines to them. Sorry about all these interruptions, guys. Okay, so Amsterdam Density Functional is a density functional code specifically designed for chemistry, right? So always from the 70s, the sort of point of view was that it should be useful for looking at chemistry, looking at chemical bonding interactions, looking at properties of orbitals, densities, and so on. So that's still pretty much at the core of ADF. Yeah, so this is sort of the overview slide of why you should use ADF for a specific set of problems. There's also a specific set of problems that you might want to use another code for, of course. So ADF, it's capable of treating all these elements in the periodic table, going from hydrogen to element 1118, with all electron basis sets being available for all these elements. So you can run them from single zeta to quadruple zeta. You can treat all the electrons, meaning that you can also look at the core electron properties, which is important if you're interested in spectroscopic properties. We also use Slater type orbitals, which is slightly different from what is used in most molecular DFT codes, namely Gaussian type orbitals. And if you remember from your first year quantum chemistry course, that has to do with the way that you expand the atomic orbitals. So the Slater type orbitals are the exact solutions for the hydrogenic atoms, so they have proper exponential behavior. Whereas the Gaussians, they fall off a bit more quicker, and they don't have the correct behavior close to the nucleus. So that has a number of advantages when we're looking at spectroscopic properties, has a number of disadvantages in terms of efficiency when we want to calculate certain integrals. We can discuss that later on. On top of that, we also have quite an efficient way of dealing with relativity. So it's an in-house developed ZORA order regular approximation that can be used in a scalar relativistic mode as well as in the spin-orbit coupling. So it's a component mode where you couple the spin and the orbital angular momentum. And that can be done quite efficiently and typically gives quite accurate results for most spectroscopic properties as well as bonding properties. More about spectroscopy later, but the combination of using these plate-type orbitals for all the electrons, relativistic Hamiltonian, gives you quite good spectroscopic properties, especially if you have electrons closely fitting to the nucleus, NMR, DPR, X-ray absorption. Chemical analysis is one of the things that people use ADF for. So we use a fragment-based approach. So you can look at a system, you can look at bonding interactions where two fragments come together to form chemical bonds, and to scrutinize the bonding interactions in that particular chemical bond. I already mentioned this, so we're active developers. We claim to be user-friendly. So people can, on any normal machine, they can just install the binary, put the run into graphical interface, should work out of the box. And we do have scientific support available, so if you do have any problems, we try to help you best as we can. We cannot do your research for you, of course, but we'll try to give you as best technical support as we can. But sometimes you will have to dig into the literature and see if something of a sensible approach for the system or not. Okay, so as I mentioned, there's an integrated graphical interface, and so the people at Plumed can have a look at how that works together with Rika. It's fully integrated with all the different modules, so it works for ADF as well as for the periodic DFT codes, as well as for the more approximate codes. And it's quite easy to set up the system to run the calculation either locally, or you can run it on a remote cluster on an HPC system like the National Infrastructure in Australia. And then you can pick up the results on your desktop and visualize, for instance, orbital properties, density properties, spectra, and so on. Right, so spectroscopic properties then, they range all the way from the microwaves to the X-ray. So we have all the properties related to vibrations, excited states, so usually this X-ray, all the chiral properties, so there's circular dichroism, there's vibrational circular dichroism, NMR and ESR are a few slides from that later on. Okay, so a few examples on spectroscopic properties to give you an idea of the kind of complexes people use ADF for. So here's a dye-tungsten complex. You can isolate that complex in a solid-state matrix, and then you can oxidize it and see what happens to, for instance, the UV spectrum. In this case, in blue, that's a neutral compound. That's the measured spectrum, right? So spectrum of the neutral dye-tungsten, dinuclear tungsten complex. And that's the calculated excitation value with ADF. You then oxidize it, so you get a radical cation. You get these two peaks calculated with ADF, and that's the experimental spectrum. So you can at least qualitatively understand what happens when you do get this radical cation and you get a shift into the near infrared. Of course, since it's radical, you can also calculate its magnetic properties. You can measure its EPR spectrum, and that's a comparison between the experimental and the calculated values for the principal components of the T function. Pretty good agreement again. For NMR properties, especially if you have any heavy elements, people would use ADF for that because the unique approximation or the approximations made in ADF are quite suitable for that. So we can calculate all the electrons. We have the stated like orbitals and a good relativistic Hamiltonian. In this case, it's 29 silicon. It's not that heavy, but since it's bound, it's datively bound to a platinum atom, there's a very strong transfer of relativity onto that atom. This is the coupling pattern you get. So on the top, when we calculate a scalar relativistic, maybe a scalar relativistic calculation of your NMR properties. And if we switch on spin-orbit couplings, so in the middle here, you see that you get the exact same splitting pattern as you see in the experiment. It's exactly the same. All the asterisks are related to spinning side bands in 195 platinum satellite. Exactly the same splitting pattern. It's shifted by 20 parts per million. For these type of complexes where you have very heavy elements influencing your properties of the electrons close to the nuclei, you do need a full, fully self-consistent spin-orbit coupling approach to at least get quantitatively, or at least get qualitatively good results for that. We also calculate paramagnetic NMR, so for precision metal complexes, they can span quite a long range from -400 to 1600 parts per million. You can see you can get pretty good agreement across the whole board here for a set of different metallocene complexes. The core electrons, they can also be excited in ADF, so we don't have a pseudo-potential, so you can excite core electrons. You can do spin-orbit coupling TDDFT on these core electrons. It's quite expensive calculations, but it can be done. And from that, you can calculate the X-ray absorption spectrum. So ZANAV spectrum, X-ray absorption near-edge spectroscopy, or NEXAVs, a near-edge absorption fine structure spectroscopy. We have the deeper core, so in this case, that's the L-edge spectrum of a dinuclear ruthenium complex that's used as a water-splitting catalyst. You can see you can get pretty good agreement between the experimental and theoretical measured spectrum. So these are typically good lying electrons for which spin-orbit coupling is quite an extensive effect. For higher lying core electrons, sometimes you can use an approach as a delta SCF type approach or state of transition state approach. That can give you pretty decent results, for instance, in spectra of these methyl-phthalocyanines, where you're looking at carbon and nitrogen atoms and looking at the K-edge spectra there. You can see that they're not as deep lying as the L-edge spectrum as shown in the slide before. The calculated spectrum here is the black spectrum, sort of going, putting Gaussians on top of these sticks here, and that's the measured spectrum. You can see it's pretty decent agreement for these type of spectra. With these calculated spectra, at least you can get some insight into what are actually the contributions to what we see in these NEXAVs spectra, and that gives you insight into what's happening in situ for these type of complexes. Okay, so I want to spend a few slides on modeling organic electronics with ADF. So there are a few specific properties in ADF that people use for studying these types of materials. Specifically, the capability of doing spin-orbit coupling self-consistently with time-dependent density functional theory. That's of interest for phosphors used in OLEDs, and that can also be important for dyes used in dye-sensitized solar cells. And then I'll also talk about charge mobilities that come naturally in ADF since we use this fragment-based approach. Okay, so a recent publication by our Japanese reseller in Japan, Mr. Temple Mori, who looked at 23 different transition metal complexes for which the phosphorescent lifetime was known, so it was measured in a solid-state matrix. And this phosphorescent lifetime is an important property for these phosphors as they're used in organic light-emitting diodes, so the flat screens that the big electronic companies want to make and have vivid colors. One important property is the color of your dye, so you can calculate the color of your dye using spin-orbit coupling TDDFT, and typically for that we would also want to calculate some vibrational progression. So that gives you a better sort of color shade of your dye, and that can also be done with ADF. The other important property is the phosphorescent lifetime. So once you get a triplet, right, so you generate these triplets by passing on a current, you want this triplet to give as efficiently as possible one photon. You're interested in the process where you have a triplet excited state luminescing or phosphorescing into the ground state as efficiently as possible. So you can see for the complex here on the right hand side, rhodium, that doesn't work very efficiently because it has a very long radiative lifetime. Complexes on the right hand side, so typically iridium complexes and osmium complexes. With the heavier transition metals, is stronger spin-orbit coupling, so there's a stronger mixing between the triplet and the singlet state. Those will be the complexes that phosphoresce more easily. So using this approach, you can see you can get pretty decent agreement across the board between experiments and calculated values, so you can use this approach to try and design dyes that have the right color as well as the desired phosphorescent properties. I mentioned dye-sensitized solar cells. There's a recent paper from the Italian group here, where they're looking at dyes. So again, these are the heavier, so the 5D elements, osmium complexes that absorb onto the semiconductor material. They absorb the light, and they need to transfer then the electron into the semiconductor material. So you want to be having dyes, so you want to have dyes that are as efficient as possible, absorbing all of the light. So you can see here, that's the experimental absorption curve, and this is the curve that you get when you do a scalar relativistic calculation. So you can do that with ADF, or you can do it with another code, but you don't capture here the long curve behavior, right? So you don't capture all of the red light here on this side. So for that, you would need a spin-orbit coupling approach. You can then use that in a phenomenological description of how much light gets converted, so the efficiency of the dye, into electrons, and it turns out it's a pretty large effect for these heavier element complexes that include spin-orbit coupling. So it makes a difference when you want to design these dyes. Right, so whole electron mobility, so in organic field electron resistors, for instance, but also in the OLED materials, people are interested in mobility of charges into charges in these organic materials. And the typical workhorse for that is Marcus theory. So you look at incoherent hopping model, so here in the middle, where you calculate basically the rate of transfer of an electron or a hole as a function of its electron coupling and the thermodynamic drive for that. That's on the right hand side there. Now this electronic coupling you can calculate with ADF quite easily in a fragment-based approach, and there's also a frozen density embedding approach to that, which is more flexible in the sense that you can include environment effects much more easily. So if you give an idea of what you can do, let's say you've got an organic crystal, in this case pentacene. You can see there's different orientations between, so different dimer orientations. So the hole can hop in different directions, and you can extract all these hopping directions, if you will, and calculate those as dimers in ADF. So you have one fragment here, one fragment here. They would calculate this electronic coupling straightforwardly in ADF. You get these so-called transfer integrals that go into that are a huge part of the electronic coupling, and we also include a few other integrals that you get naturally in ADF. So that's the overlap here, and these are the side energies there. So you get this electronic coupling quite naturally in ADF. Once you've set up your system where you have two fragments, so two dimers, that can then calculate the whole and the electron mobility. An example of that, quite a while back, so that's for the exact same crystal, that's pentacene. You can calculate all the mobilities in all the different directions, shown here on the top left. You can calculate the mobility for each of these directions, and you can plot them in a polar plot, and you can look at the anisotropicity of the whole mobility in this case. Those are calculated values in blue here, right? So that's what you calculate when you use the dimer-based approach in ADF, and those are the experimental values. So you can see those calculated with ADF are a bit higher, but you get at least the right function and you get the right and statistically out of the calculations. Can you guys still hear me in Sydney? Because I noticed there's a bit more noise here in the background as they're setting up a conference here, so I do apologize for that. Another application of this fragment-based approach is that you can look at these processes where you have a singlet excited state and one of your fragments that can then couple into two triplet states on those two dimers. And there's a mediated mechanism where you have a charge transfer state in between. There's a charge transfer state in between, and then that can couple to a triplet state. Or there's a direct pathway where you have two electron coupling between the singlet state on one fragment and the bound state on the other fragment. You can calculate all these pathways, for instance, for a set of different configurations, and you can plot how large the coupling is. So if the coupling is very efficient, you can generate from one excitation, one singlet excitation, you can actually generate two excitations, so two triplet excitations. So you could get an efficiency, a solar efficiency of 200% if everything works perfect. And for some of the orientations of the dimers, indeed you can get an efficiency of generating excitons over 100%. Okay. So moving on to advanced solvation and environment, so there are various ways that you can of course treat your larger system or include some sort of environment effect on a specific part of the system you're interested in. I'll talk a little bit about QMMM approaches that have been in ADF for a long time but haven't been developed much. Talk a little bit more about frozen density embedding or subsystem DFT, and I'll highlight sort of the developments that are going on at the moment in ADF in terms of Python tools for running QMMM, QMQM type of calculations, as well as doing workflow. And there's quite a unique feature that's related to molecules absorbed onto metallic nanoparticles, so I'll give you a slide on that as well. Right, so QMMM, there's two ways, two divisions of doing it. One is the additive scheme, where you just add your QM energy to your MM energy, and you make sure that if you break a bond, that you try and capture the interactions between the QM and the MM region as best as possible. And there's different variations in the theme and also different ways of dealing with the electrostatics there. But by and large, that's the additive scheme. It's a fairly standard implementation that was pretty early, but it hasn't been much developed since. And then there's also a subtractive scheme through Quilt, so that's a program developed by Marcel Swart. And that's based on the onion type approach that people might be familiar with. And the implementation by Marcel is highly flexible, so you can have many different types of setups, so you can have different regions embedded in each other. And then you can have 3 layers in this case, or you can have much more complex setups where you treat all different regions at different levels. You can do everything at the QM or different QM levels, semi-empirical levels, molecular mechanics. You don't need to use ADF as a QM, so you can also use semi-empirical. There's an interface to ORCA there as well. It's quite a powerful code for doing QM-QM type of calculations, QM-QM and QM-MM. I mentioned that we have a EU project where somebody's working on this, so we're trying to develop more QM-MM functionality, so that's how Hansel is working on that. And also making it easier for people to set it up, as well as analyzing these types of calculations. Frozen density embedding, or subsystem DFT, is essentially a DFT and DFT approach, or QM-QM approach, if you will. It was developed in the 90s by Aya Washoe, who of course got awarded the Nobel Prize last year, together with Tomek Veselowski. Veselowski, that was one of the first real implementations of that. And they call it frozen density embedding theory, others call it subsystem DFT, frozen density embedding as we call it. So you will find different names, but it's essentially the same approach, orbital free DFT, of something as variation on the theme. So what is it? Let's say you're interested in the properties of a molecule that's solvated, in this case in water. So that's aminofumarain here in blue, that's solvated in water. Now you can set up a subsystem in the subsystem DFT approach. For instance, you can have aminofumarain surrounded by a few water atoms. You can have all the other water atoms being their own subsystem, right? So you have one fragment here, the blue and the red, you have one fragment here, that's the green. And then all these densities are calculated separately on each fragment. So you do a DFT calculation on a small fragment, each one of these fragments, but all these fragments are also allowed to interact with each other, so they can polarize one another. And you can do this in multiple cycles, so you can freeze one fragment and freeze the other, and do that until you reach self-consistency. It's a freeze-thaw approach. This was quite a feat about 10 years back, 2005, when they managed to do this type of calculations on aminofumarain using time-dependent density functional theory within the subsystem approach on 1,000 snapshots that were generated with molecular dynamics. And through that, they were able to reproduce the experimental blue shift of 0.2 eV when this molecule is solvated from water. We still need to do 1,000 of these TDDFT calculations, so it doesn't come for free, but it can be done, and of course nowadays on the present day computer, it's even better because you can run 1,000 calculations in parallel and have perfect scaling for that. I just want to highlight that there's also been an application where you use a solvation model based on statistical mechanics. It's a three-dimensional reference interaction site model. You can also do that in ADF, but it's even more an expert option. But if you're interested in learning more about that, then I can give you some information later on. And in that case, you just need to do one calculation. They have the average solvent structure at the force field level that takes into account the polarization of your environment, the average solvent structure surrounding this. Now, this frozen density embedding is highly developed in a few groups. So one is the group that we still share a hallway with the electrochemistry group in Amsterdam, that's the Fission. There's a group in Münster, one is Neugebauer, and there's a group in Karlsruhe, Professor Jakob, as well as Michele Pavanello. I'll show an application from him later on in Rutgers University in Newark. Okay, so just to give you, we can not only do solvent shifts, to give you an example of other things you can do. So you can look at charge transfer, more on that later. You can localize spin densities, and what does it mean, localized spin densities? Let's say you've got a dimer complex here, where you have a radical, and DFT is well understood why it does that, but it tends to delocalize that radical over the two.
Who's afraid of dying?
It tends to delocalize the radical over the two aromatic units here, and even if you include self-interactions, the self-interaction corrected, it doesn't really remedy that problem. If you use complete active space approach, then you can see you get a proper localization of the spin on one of the two states, or one of the two dimers. And of course, there's a state that's close by where the electron is indeed sitting on the other unit. Yeah. So viewer 24, rest will make the presentation download it all. So there's no need to write down all the references. I'll put on the PDF later on, probably early next week. And so through this phase and density embedding approach, you can essentially localize things like spins, charges, etc. In some respect, that would be better than classical DFT because you can do things that classical DFT cannot do because it has this well-known over-delocalization problem. They can also be combined, phase and density embedding excited states with state selection. So if you're interested in molecules, for instance, pyridine on a gold cluster as a standard example, if you're interested in what happens to a certain type of excitation as a function of molecule nanoparticle separation, you can zoom in on that specific excitation on the subsystem, and you can see what happens when you move it closer to a nanoparticle. More recently, so let me just go to this slide first and then back to the other slides. More recently, within the phase and density embedding framework, spin-spin coupling has been implemented already. It was implemented a few years back, but now it's available in the public version as well, where you can look at NMR properties, in particular spin-spin couplings, and see what happens when you solvate the molecule. And typically that can have a quite strong effect on spin-spin coupling. And so here's a table for solvent-induced shifts of spin-spin coupling constants, where you have a molecule A solvated by a molecule B. So molecule A solvated by a molecule B. This is when you do the full calculation, right? So when you do the full DFT calculation, these are the spin couplings here, and this is when you do the phase and density embedding calculation. And what this M means is that you basically extend your density on a monomer basis, and the S means that you extend your density in the full basis of your system. It's slightly less efficient, but it's still cheaper than doing the full calculation. And so for the hydrogen fluoride dimer, you would need to expand the density in this full basis, and you need to do three cycles to get agreement, get qualitative agreement with your PDFT calculation. So the other complexes described here, so ammonia water and water dimer, actually can get away with just a few 3-4 cycles, maybe one will be sufficient in a monomer basis, and you can get pretty decent agreement between the full DFT values and the subsystem DFT values. But that's now possible in ADF. It's still quite an expert option, but if you have any questions, then we can try and help you out with them. Okay, so back to this slide then. So within this phase and density embedding, I mentioned that because you have these subsystems, you can basically constrain or localize things like charges, excited states, and spins on one of the two or one of the more subsystems. So let's say you're interested in this charge hopping again. You have this fragment-based approach in ADF. You can do the same within the subsystem DFT. You localize your charge on one of the monomers, and then you see what happens if you have this charge localized here in the bra, and this charge localized on the other unit in the kit. You get your diabatic hemiconium, and you diagonalize that, you get the electronic coupling out, and that then goes into Marcus theory for getting out the mobilities of charges in these types of materials. You can do the same thing with excitations. So you can look at the coupling between the triplet excited state on one fragment and how that couples to a triplet excited state on another fragment. And that coupling, so that electronic coupling, is related to the propensity of an exciton to move through a material. So in the Marcus type of approach, you can then calculate the mobilities of these excitons through a material. And ideally, you want to be able to describe the whole process on the same footing, so that's what these two groups are working towards, the Pavanello and Rutgers group. So Pavanello, Rutgers, and Neugebauer and Münster, they're working towards a unified description of where you excite a molecule so from the ground state to the excited state. It can then either from an excited state that moves around, or it can move its charges, so you can get a charge separated state. That's a recent publication written down here, long range charge separation. And then you would also ideally be able to describe the charge moving through a material within the subsystem DFT. One of the advantages of the Phosphorescent density embedding is that linear scaling with respect of the subsystem. So if you're interested in the environment, which of course can be highly polarized if you have a charge, you can add on more subsystems that can then respond to the charge moving from one unit to the other. And that can have, depending on how polarizable the system is, have a strong effect on the mobility. Okay, so QMMM, I mentioned this is something that we're working on. So we're a PhD student working on Python tools for making that more amenable, more usable. And one of the applications is looking at is when you have molecules that you want to dock inside a protein. And so for these docking type of applications, typically what people are more and more interested in is getting more accurate scoring. So one would need DFT-based calculation, or we start out with a semi-empirical calculation. And for the top hits, so the best binding ligands, you want to refine with DFT. So you want to make sort of an automated approach to put inside a molecule, inside the binding pocket, and then within that pocket you can do, for instance, the subsystem DFT approach, or subsystem DFTB approach, calculate more accurate binding energies, and then you can think about refining that even further for your top hits, etc. So ideally you want to have a more or less easily automated approach or flexible approach, and so the tool of choice for that is Python. And so we have at the moment we have different Python modules, but we're trying to merge them together into a unified platform that can allow you at a high level basically to set up your job and do multiple things. So for instance, you can first define a number of complexes or molecules that you want to calculate. For those, define what you want to do. Do geometry optimization with a small basis, then maybe you want to do a single point calculation with a larger basis set, and finally you want to get a property, let's say, NMR shieldings, and you want them to tabulate them nicely into a table or XML file or HTML file that you will read out. So that's what we're working towards, and so this is one of the focus areas for the next few years. There's also advanced tools for doing, at the moment, molecular dynamics as well as QMMM type of calculations. Again, it's a Python tool. It's called FlexMD. It's developed so mainly by Rosa Bulo, who's now at the University of Utrecht in the Netherlands. And she's particularly interested in running adaptive QMMM. And so adaptive QMMM is where you have a system where you have flexible molecules that can move basically from your QM region, so your area that you want to describe at the DFT level in our case. But they can move easily from the QM region to the MM region. And when that happens, you typically have a problem because you basically need to deal with the boundaries between the QM and the MM region. That's known as sort of 5 different approaches to sort of treat that problem. So you want to adapt basically your QM-MM division, the division between the QM and the MM region, to make the transition as smooth as possible when molecules go from the QM region to the MM region and vice versa. There's a recent review paper on this, so it's called Multi-Scale Modeling of Chemistry in Water. Are we there yet? It describes all these 5 methodologies that are available with this Python tool that we ship with ADF, and each one of them has advantages and disadvantages. So unfortunately, there's no unique approach that can tackle all of the potential problems that come along with running these kinds of calculations. And through this Python interface, we also hook into Plumed and ASE that will allow you to do advanced things like running hyperdynamics and metadynamics, and you're interested in running accelerated dynamics. That's one of the things that we also want to develop in our own platform, so it's much more easy to hook it into the different codes. So not only ADF, but also the more approximate. Okay, just 3 slides on this other advanced environment, something completely different. is molecules on nanoparticles. So let's say we're interested in the excitation properties of a molecule sitting on top of a large metallic nanoparticle. When you're looking at the excited states of this molecule, obviously the metal particle sitting beneath it is going to affect those excited states to a large extent. We want to take into account ideally what happens for the entire nanoparticle. If it's metallic, there's going to be there's a huge effect of all the atoms sitting there, which you cannot dream to address at the TDDFT level for particles as large as 2,000 atoms. So what Dr. Jensen at Penn State has done is basically use an approach where you can treat the response at the atomistic electrodynamics level, but using a force field-based approach, a polarizable force field. So each one of these atoms here got a little dipole moment, and it's a little capacitor. You can calculate that in the DFT data using DFT data in the build, match those properties as closely as possible. And then you can take into account how the response of a nanoparticle couples to the excited state properties of the molecule. So you use it as an embedding potential self-consistently to look at the excited state properties of the molecule. And from that, you can calculate interesting properties like surfaces in Hamilton or surfaces in Raman, hyper-Raman scattering, like plasma-exciton hybridization, and all sorts of interesting things like how the photochemistry is affected if you have a molecule observed onto a nanoparticle surface. Again, there's a recent review that gives quite a fairly good, understandable view on what it does and what it can be applied to. One example then, so if you have, I think this is a DNA base absorbed onto a silver nanoparticle, its transition dipole moment is in this direction. If it's aligned with the surface plasmon, if it's vernacular to the surface plasmon, you get a reduced absorption. That's a different scale here for the polarizability. Whereas if it's sort of in parallel with the surface plasmon, so the transition dipole moment is in parallel with the surface plasmon, you get a hugely enhanced absorption. So you can see it's a factor of 6 with respect to the two different orientations. But for the hyper-Raman, it can be even much higher orders of magnitude difference between different orientations. Okay, the chemical analysis then briefly, and then I'll move on to Dan, the periodic DFT approach. The approach always has been in ADF that chemistry happens when atoms come together, right? So we use atoms as a fragment, but when we're interested in chemical bonds, we can use the two parts that form the chemical bond as a fragment and see what happens when the two come together. Quite an old review on that. There are some more recent reviews, but that's from Matthias Dickelhaupt. That's one of the persons that has used this and still is using this approach quite a lot. It allows you to look in great detail what happens when the two fragments come together and start forming a chemical bond. And you decompose basically the energy of this chemical bond into different things. What's important here is this interaction term, that through this energy decomposition, which comes from extended transition state theory, so ETS, so you will see EDA, energy decomposition analysis, interchangeably with ETS, which stands for extended transition state theory. You decompose the interaction energy when the two fragments come together by switching on the different interactions run at the same time. So you don't have to do that, ADF does it for you, so you get all the energies printed, but that's the way it sort of works under the hood. So first you allow the two densities to see each other, that gives you this electrostatic term, so the two densities are allowed to polarize one another. That's typically attractive. Then you switch on orthogonalization, so that gives you a Pauli repulsion term, with basically interactions between the built orbitals that's related to the steric interaction, so that's sometimes also called the steric term. And then finally, you allow the orbitals to relax in the bases of those two fragments. And that's a stabilizing term for the orbital interaction. When you have a nice symmetrized fragment, that orbital interaction term is decomposed according to the different symmetry representations in the group. And so, for instance, that can give you insight into pi, sigma bonding interactions, and so on. A few years back, there was an extension of this approach, so using energy decomposition, but looking at the orbital interaction decomposition from a different point of view, namely by using natural orbitals for chemical valence. And that then allows you to scrutinize the bonding interactions in more details by looking at the deformation densities when the two fragments come together. You can also view this orbital interaction term as basically a charge transfer, right? So how charges move when the two fragments come together, so electrons go from fragment A to B or vice versa. You can also apply, you don't need to apply it to minima, you can also apply it to position states or even across reaction coordinates. So here's an example where experimental results were with rationalized. They're using DFT calculations, using this energy decomposition, looking at palladium catalyzed alylation reactions. Now you can then scrutinize what goes on inside the transition state. So there's quite a fine balance there between the steric interactions and the electrostatic interactions, as well as the orbital interactions. So you can try and tweak the ligands here to basically destabilize your intermediate here, that will lower the activation barrier, so making it better. So you can use this type of approach to fine-tune basically the interactions that you get in the transition state, and thereby rationally designing catalyst, if you will. You can also apply the ETS-NOCV approach to a range of different complexes. So there's lanthanide and lutetium complexes, and there's an application from a few years back looking at carbonates and see what happens basically for the different type of complexes in terms of flowing charge from the transition metal onto the carbonate ligands. There's a difference between the lanthanide and lutetium in this case. It's also been applied to biomolecules. So there's the AT dimer here from DNA. Total interaction energy is 13 kilocalories per mole, which you also get with a different approach, and it's similar to what you get in the experiment. But then you can scrutinize this bonding interaction using ETS-NOCV. So you get your orbital term, you get your steric repulsion term, and you get your electrostatic attraction term. And this orbital term mainly has three components that you get from these natural orbitals of chemical valence, and therefore related. The two largest leading terms are related to the hydrogen bonds here. And surprisingly, what this means, the NHN hydrogen bond is the strongest interaction. So that's around 13 kilocalories per mole. That specific interaction gives you a stabilization of 13 kilocalories per mole. So it's quite strong for a hydrogen bond. The hydrogen bond here on the bottom, so that's NH donating into a carbonyl group here, is about half of that. And then there's another small contribution from an orbital interaction. It's more related to charge transfer from thymine, from adenine to thymine. Since we use density functional theory with everything on a grid, it's quite easy to do all sorts of grid-based properties such as atoms and molecules. So you can apply that to molecules as well as to surfaces. There's all sorts of other density-based properties that you can calculate quite straightforwardly. Okay, moving on then to, unless there's any questions at the moment about ADF, we can do that at the end as well. Then I'll move on to periodic DFT. So that's our code, it's called band. It's very similar to ADF, but it can handle periodic band recognitions. So you can replicate your system either in one dimension, that's related to nanotubes, or carbon nanotubes, or inorganic nanotubes. You can apply to surfaces, so in 2 dimensions you get your surface represented in proper 2-dimensional boundary conditions, and of course you can also apply to bulk systems. Okay, so since we have atomic orbital-based code, there's a few differences between the plane wave code. So there's orbital-based codes and there's plane wave codes. The latter being more prominent, at least in the solid-state physics community. So I just want to highlight a few advantages and disadvantages between the 2 approaches. Okay, so an advantage of using atomic orbitals is that you can do, at least in ADF and band, you can use the exact same basis set, exact same settings for integrating your density, and thereby you can compare your molecular system, the cluster approach, with a periodic system. Right? So you can calculate properties, energies, NMR properties, and so on for the bulk as well as for the cluster approach. And from that, you can get a good view of what periodicity does in terms of binding energies or properties. That's one clear advantage of using an atomic orbital-based code. The other thing is, I mentioned we do have all the electron basis sets for all of the elements, so we don't have any problems that could arise from using a pseudopotential. Don't get me wrong, pseudopotentials make your codes much more efficient and they're typically quite good, but sometimes you can get some artifacts arising from using the pseudopotentials. The plane wave codes are typically quite efficient, so for bulk systems where you have lots of electrons, the plane wave codes will typically be much faster than an atomic orbital-based code. However, if you have empty systems, zeolites, where you have a lot of vacuum, or you have a 1D or a 2D system, the atomic orbital-based codes can be much more efficient because you don't need to fill the vacuum with your plane waves. Also, in some cases, you can get some artifacts from using a 1D or a 2D representation in your plane wave code, where you need to repeat your system in all the dimensions because you always need a 3D representation. Again, because we don't need to reproduce the system in the 4th dimension, you can apply continuum solvation, so you can look at solvation effects of surfaces or molecules absorbed onto surfaces. You can include continuum solvation on top of that. You can apply a homogeneous electric field. I'll have a slide on that later on. And since we do have atomic orbitals, you can do all the analysis quite straightforwardly without having to fiddle about transforming them to localized orbitals. So you get, quite naturally, you get all the orbital populations out, you get your crystal orbitals and so on. Again, since we have all the electrons, you can calculate 4 electron properties quite straightforwardly. Okay, so just an example from the recent literature, where I think it's quite important that you use a 2D representation, is where you have molecules, where you have surfaces as a support, you have your metal absorbed onto the support, and then you use that as a catalyst. And it turns out that quite often the support has a strong effect on catalytic properties, as has been well known, of course, in people doing heterogeneous catalysis. And the reason is that the support is not inactive. The reason is that the support can actually donate charge or take charge away from your metal particle absorbed onto your surface. So whenever, for instance, in this case, there's methane or hydrogen activation on nickel, on alumina support, for the different transition states that you can have, there's a strong electron transfer from the support into your nickel atom. And that actually polarizes your surface. So if you reproduce your surface in the 3rd dimension, you need to think about how you deal with that. And there's approaches for that, so you can use dipole correction terms for that. But ideally, you would be able to describe the polarization of your surface within 2 dimensions. Then, as an atomic orbital-based code, had some issues that we're trying to fix. So there's Mirko Fonchini, the PhD student I told you about in the beginning. And he's addressed some of the technical issues that made bands pretty slow for some type of applications. So what it means technically, we use a different fitting approach, so this so-called ZLM fit, which is easier, so it's quite easy in terms of code. It's quite easy to do, and it's more easy to extend it to a higher order in the fit functions. It's linear scaling with respect to the number of atoms, so it will allow you to assess much larger systems, and it's also more accurate in terms of gradients, so you can run geometry optimizations more robustly. There has been the focus for bands in the last year, and now you can treat unit cells where you have 1,000 atoms, 7,000 basis functions. You can run geometry optimizations on a decent sized cluster. So that can be done now. So for the next few years, we'll be focusing more on more efficient algorithms for finding position states. We're also looking a little bit at interscaling, so trying to make it scale much more favorably. That's one of the areas where there's a little bit more to be there. So it's one of the things that we're looking into at the moment. A few examples then. So within band, you can also use the same ZORA Hamiltonian, but it has a scalar relativistic approach. You can use spin orbit coupling. You can do fully self-consistent spin orbit coupling. Other codes can do conservative spin orbit coupling. But we can do fully self-consistent during the SCF. And as an example here, so this is a density of states of lead oxide. And if you have the lead oxide couple, that goes in your car battery. So when this paper was published, 2011, basically the media pitch for that was that Einstein makes your car start. But we narrowed it down a little bit. We say relativity makes your car start. So what happens? You can switch on relativity in ADF, so you can use a non-relativistic treatment. And this is the density of states that you get. And of course, in order to get your electron moving around, you need to move it from the valence band into the conductance band across the Fermi edge, and they're quite far apart. So if you then switch on scalar relativity, that stabilizes the 6s electrons. They consequently also the empty 6s orbitals. They come closer to the Fermi edge, so it's easier to move electrons from the valence to the conductance band. Then finally, if you switch on spin orbit coupling, that still has quite a succinct effect on the density of states of the valence band. So those are the 6p electrons of lead. You see you get a build-up of density of states closer to the Fermi edge, making it easier for electrons to become conducive. So if you didn't have any relativistic effects, you would need a battery 5 times as large to get your car started in the morning. Right? So the voltage you would calculate would be 2.4 volt for non-relativistic, 12 volt for spin orbit coupling. Okay, so you can visualize all sorts of things. For instance, electron localization function. You can localize, you can visualize local density of states that correspond to SPM images. There's an example here. Of course, you can visualize band structures as well. So for chemists like me, it's actually quite nice to also see the WAN zone, so you can see how the integration in K-space corresponds to your path in the very WAN zone. Yeah, so of course, sometimes you want to do surface chemistry, so you need a functional that works well for chemistry as well as for bulk systems. So one of these functionals is FTPSS that does well for optimization energies as well as for lattice constants. But there are a number of other functionals available in ADF as well. So one thing that I want to highlight is that we have the Brinner dispersion corrected functional, so the D3 dispersion correction functional in ADF band. And so with that, you should, that's been implemented already a few years back, but you should no longer use the Brinner D2 corrections. Right? So here's an example of why you shouldn't do that. This organic molecule absorbed onto a gold 1-on-1 surface. This is the Brinner D2. dispersion correction, so they're obsolete now, if you will, and they tend to overbind, right? So this is the binding curve with degree 2. That's the experimental binding distance to the surface. That's the degree 3 curve over here. So in blue, that's the degree 3 curve over here. And that tends to give much better results with respect to experimental findings in terms of bonding distances as well as bonding energies. So you should always use the D3 Gröner corrections, according to Stefan Gröner himself. In ADF, we also have different approaches for dispersion corrections. So there's the density-dependent dispersion correction. That's one on column above. It's available in ADF. In ADF, we also have the many-body dispersion functionals by Pachenko and Scheffler. So there are different approaches to try and capture this dispersion interaction in DFT. Right. A few slides on the band gap problem in DFT. Right? So it's well understood that if you want to calculate the band gap for a solid state material, inorganic semiconductor, you always underestimate this band gap. Essentially, it's not a surprise because when you use sunshine DFT, you have the so-called integer derivative discontinuity in the exchange correlation potential. What you need to do is you calculate the band gap. You look at the Kanchan band gap, which is of course the difference between the ionization potential and the electron affinity. You just add this derivative discontinuity, so delta X term. But it's not straightforward to calculate. So there are a few solutions that have been around, and the most satisfying one is, because it's theoretically sound as well as typically giving good results across the board, is using many-body perturbation theory, so TW theory. That's not available in bands, and it's available in a few other codes. But it tends to be quite expensive as well, so you can only run very small unit size for that. It's something we'll be looking into in the future as well, because there have been some advances there making that also faster in the so-called G0, W0 approach. Another solution might be to use hybrids or streamed hybrids. They have percentage of Anisotropic exchange, and why does it work? Well, Anisotropic doesn't have this integer derivative problem, a discontinuity problem. So some people would say it's a fudge, other people would say that's also a perfectly valid solution. We don't have hybrids in band yet. It's one of the things that's on the plate for the next release. So we're working on that. For some transition metal oxides, you can use a Hubbard potential. That essentially what it does is it localizes the DNF electrons and it fixes the band gap problem. But sometimes that gives rise to wrong density states. So it's not necessarily a good solution for all problems. The other thing that can be done is use a model potential, and there are two model potentials that are available in band. And we use a orbital effective potential like exchange that's related to Anisotropic exchange, but it's not the same. One is based on a potential from Becker and Johnson that's been modified by Pan and Blaha that has been explicitly fitted to band gaps. You can apply it to bulk systems, and with a little trick, you can also apply it to 2D systems, but that's not natively in the theory, so it's not been well tested. Then there's another functional that's been sitting around in ADF for a long time, so it's developed essentially in Amsterdam by Gutsenko, Valera, Olympic, and Brians. That has been dusted off by a physics group, and they slightly modified the correction, so the correlation term, so that's solid correlation. And this functional that's not useful in ADF because it's been superseded by a statistical average of orbital populations functional, but it turns out to be quite useful for inorganic semiconductors. That explicitly includes this missing term that you get in Kanchan DFT. They can apply to bulk as well as to 2D systems. So for 2D semiconductors, that can be applied as well. Okay, so Pan and Blaha modified this Becker-Johnson potential. Those are the red dots here. comparing theoretical band gap to experimental band gap, you can see you can get pretty decent readings calculated on the experimental band gaps. The pink process here, that's the GW approach, and you can see, of course, that's also satisfyingly given quite good results. HSC, that's a screened hybrid, that's also quite good, with a few outliers, but that typically also tends to be quite a functional approach to these type of problems. So we don't have these available in ADF, but we do have that available in ADF band. The GLB then, that's another potential, and that tends to give quite good results for inorganic semiconductors. Hasn't been as widely tested, so mind you, it hasn't really been reoptimized, so it's functional and hasn't been lying around, just looking for a different correlation potential using the exchange part of GLB. So there are a few semiconductors here, and we can look at the calculated band gap. And you can see there's a difference here for the GLB, where you basically shift your valence band, so you can conductance band. Depending on where you are in the case space, the correction, which is the red term here, can be larger or smaller. So it's not an equal, it's not just an additive term. It depends on where you are in case space. This exchange derivative discontinuity is not a trivial term, but it's calculated for every different point in case space. Okay. So there's a typical picture that you get. So this is gallium nitride. That's the experimental band gap here at 3.2 eV. The GJ underestimates that. So if you use either one of the meta potentials, you actually will overestimate this experimental band gap. But then if you switch on relativity to the scalar rate efficient approach, you can see that for either of these approaches, you can get pretty good results in agreement with the experimental band gap. So you need the two things. So you need an approach that deals with the band gap properly, the meta potential from the GW, and you also need to treat relativistic effects properly. Right? So for some cases, the inorganic, organic hybrids, solar cells, so the lead iodide methylamine hybrids, are quite hot now. For them to understand really what's going on in the band gap, you need a good way of actually treating this band gap problem, and you also need to know the problem. So you need both to really understand what's going on. Okay, so then, as I think I promised, there's one application where you do need the 2D approach when you apply an electric field, in this case, to two-dimensional semiconductor. So in this case, is molybdenum sulfide. We apply electric field across the surface, so it's a homogeneous electric field. What we do, of course, is you start polarizing the surface. And through polarizing that, you basically stabilize the conductance band. So you can see here at zero field, there's a band gap of 1.6 eV. And if you start switching on the field, and you go to a field as high as 6.5 volts per angstrom, you actually close the band gap. And that's expected behavior. It's also what you get out. When you do your calculation in band, or you do your calculation in another atomic orbital based code, which can treat the core electrons properly, you get the right behavior. If you use any of the plane wave codes where you need to apply a sawtooth potential rather than a homogeneous electric field, you get the wrong behavior. So for these type of applications where you're looking at two-dimensional semiconductor materials, you want to understand the behavior under electric fields, you do need a 2D approach to get that right. Okay, so I've been waffling on for a long time now, so I'll briefly zoom through what are methods that we have aside from ADF and band, and then we'll do Q&A, and then for people in Canberra, I'll hand you over to Richard. Okay, so DFTB and ReaxFF are two modules that we're working on quite extensively through academic collaboration. So our developers, they come mostly from the density functional side. So through academic collaborations, we're now developing DFTB and ReaxFF. The DFTB, in a nutshell, what it is It's related to a semi-empirical approach where you have only nearest neighbor interactions and you have a minimal basis set. And when you have that approach, you can solve the secular equations. It's just the Hamiltonian matrix and the overlap matrix. But in DFTB, you look up, basically you pre-compute all the Hamiltonian matrix elements and the overlap matrix elements for every pair that's sitting in your system. And in principle, you use DFT data for that, so that's why it's density functional based. So you do a DFT calculation on a set of pairs, you calculate the data for the Hamiltonian and the overlap. You look them up in the table as you need them for a particular molecular system at hand. And from that, you can get all the properties you can get from the quantum mechanical approach. So you can get charges, energies, orbitals, properties, and so on. It seems straightforward enough, but it turns out it's pretty tedious work to do all of this parameterization. So in that EU project that recently finished, in fact I finished 2 days ago, together with Heine's group, Rutgers University, we set out to actually make parameters, DFTB parameters for all of the periodic table. And we succeeded to that in some extent, and on top of that we also managed to include a few more properties. Now in this parameterization you can put anomalous interactions, or you can add it separately, you can include relativistic effects and so on. So you can put a lot of things into the parameterization that will then make it easier to calculate the properties of your fully interacting system. So the current capabilities in our implementation of DFTB is that you can do second order DFTB, so where you set up your Hamiltonian, you also look at self-consistent charges. So in the calculation of the Hamiltonian, of course the Millikan charges go, and Millikan charges are then calculated self-consistently. And then there's also a third order approach to that takes into account a little bit also polarizability. So that's possible. You can calculate it for molecules as well as for any periodic system. Since it's essentially atomic orbital based, you can also apply it to 1D systems, 2D systems, 3D systems. You calculate frequencies, pheromones, density of states, band structures, population analysis, of course, and since this release, you can also calculate the phase set parameters. There's a simple 1D driver there that allows you to run molecular dynamics with DFTB, since it's roughly 1,000 times as fast as the DFT approach. That's fairly doable even on a small size computer. Fully integrated that into our graphical interface, so it can easily be used, for instance, as a pre-optimizer for running these DFT calculations, like for molecules with ADF or for periodic systems with band. Okay, so I mentioned the problems with DFTB is having all these parameters. So in the publication last year, we have all the parameters for most of the periodic table, but that's only the electronic part. Right? So that allows you to assess electronic properties, for instance, band structures. You can see in this case there's a good agreement between the DFT data that you put in and the parameterized DFTB data that you get out for germanium silicons, or zinc length structure for that. This parameterization has been sort of fully automated, so if you then want to parameterize against a different functional, for instance, another potential that gives you right band gaps, you can in principle redo the parameterization if you understand the script. So we're currently working on making that more usable so other people can do their own parameterization as well. At the moment you can use all these electronic parameters that we ship. We're working also on the repulsive parameters that you need basically to get the forces out. So you can do, when you have repulsive parameters, then you can do your dynamics, like frequencies, do geometry optimizations, etc. So at the moment, if you want to do dynamics or anything geometry optimization related, then you're stuck to the old set of parameters that we have, which is the Grayson set, originally with the parameters from DFT.org, which is free of charge if you're not-for-profit organization. So these DFTB, the raw parameters, they're fairly limited, but they're set, for instance, for the organic elements that will allow you to do, biosystems and organic systems, and there's also steps for metallo-organic frameworks, etc. But you need all the parameters for every pair that's available in your system. So if you pick a random few elements, you need to make sure that you have a parameter set available for that. We do have a way to automate this recursive parameters, and sometimes we have them, they're available, but they're not yet in the useful state in the sense that they don't give good geometries for any set of elements you can pick. Alright, so then in 2014, Robert Huber implemented the time-dependent extension of DFTB that allows you to calculate excitation spectra of very large molecules such as the all-electrons. Alright, so let's calculate the spectrum here. Let's see experimental spectrum there in the best phase. Notice the scales are not entirely the same. But yeah, you get roughly, in this case, you get roughly the good shape. It's slightly condensed with respect to the experiments, so slightly squeezed together, and it's off by about 10 nanometers or so, which is not bad altogether. Another application that the Jacobs group, so the Hanna group in Jacobs is working on, is looking at then the semiconductor materials and seeing what happens if you have defects. So it could be atoms missing in a two-dimensional semiconductor, or in this case it could be if you sort of squeeze your system or you ripple it. And using non-equilibrium Green's functions coupled with these electronic parameters, you can calculate charge transfer properties, so transmittivity of virtually all the elements in the periodic table. Not surprisingly, the electronic connectivity of these materials depends quite strongly on the defects in the system. So depending on how much you ripple your system, so if you get larger unit cells, you get much better connectivity because the system is much better performed. It's also been applied to nanotubes, so a single-walled and multi-walled nanotubes, and then see what happens to the connectivity if you apply pressure to squeeze the tubes together and how that affects connectivity. You can imagine that if you squeeze the tubes closer together, it's easier for electrons to go from one to the other. And that's exactly what you see, as in this case, you see the band structures when you compress the system or decompress the system. And you can, on the same paper, there's calculated the conductivity using NAGF. Okay, so DFTB we're working on a little bit, so mostly together with the Heine group. We're looking at implementing more advanced MD drivers, so doing von Oppenheimer molecular dynamics as well as excited state dynamics, AFF dynamics, and real Neumann. Looking also at the surface hopping, so systems can evolve in different excited states. Ideally, we'd like to include spin-orbit coupling, so then you can look at systems going from a triplet to a singlet state, and that relates, of course, to persistent crossing. One of the things that we actually wanted to do in the previous review project, but it turned out not to be so trivial, is have the DFT embedding in DFTB. So a 2M type approach, where you have the reactive system that you treat at DFT level, and it's polarized by the environment that you can treat at DFTB level. And we're still working on making better tools for making all these parameters that you need for DFTB. There are also other approaches available. Again, everything is nicely integrated in the graph interface. So we have universal force fields, we also have MOPAC available, and all these approaches can be used within the same graph interface. The MOPAC, also semi-empirical code, developed by Jim Stewart. So in 2012, there was a new parameterization, PM7, that supersedes all the other parameterizations. It should be more accurate, at least for...
Yeah, very good, Joshua. Where did you go?
Sorry?
That wasn't us.
Ah, okay. I'm sorry. As I mentioned, I'm easily distracted. So this PM7 that's supposed to be more accurate in terms of thermochemistry. Also, more recently, there's been significant speed-ups. That has been done mainly by a group in Brazil, but now also we have the source code available, so we can pilot ourselves. It's been parallelized using OpenMP, so that's pretty straightforward parallelization. It can be done better, but it's not really necessary. I think it's quite efficient as it is, by also making use of the Mark kernel libraries and the Intel compiler. So last year, it's actually, for decent-sized systems, it has become 100-fold as fast as it was for previous versions. So you think about creating pretty large systems with MOPAC now. I would say up to a few thousand atoms, quite straightforwardly.
Joshua, you want to eat a bit of this one?
Okay, so ReaxFF then has sort of a new module that has been added 2 years ago through collaboration with Anisotropic. And it sets itself, ReaxFF sets itself the grand challenge to tackle engineering challenges at the optimistic level, right? So if you want to understand what goes on inside a chemical plant, ultimately you would also need to understand what goes on at the atomistic level. There is an example where you have an aluminum tube that oxidizes ethylene in an oxygen ozone mixture. If you want to understand the dynamics of this, you'll be hard pressed to run any sensible DFT calculations in those kind of systems for any sensible time scale. So you need a faster approach than DFT, and probably you also need a faster approach than DFTB. Same goes for fuel cells, so that's one of the applications that other combiners are actively working on. There are a lot of processes going on at the same time between the electrodes and the electrolyte. You need to understand all of the processes at the atomistic level. So what do? If you can define DFT, so you apply a force field-based method, so atomistic potentials. Classically, you would have a harmonic potential. So for instance, you would describe a stretch as a force constant multiplied by a parabolic function that describes the displacement with respect to the equilibrium distance. Of course, if you have such a description, you cannot break up one bond, so it was already realized in the early 70s that you need bond order potentials. So you need a way to take into account this bond order term in all your bond, angle, as well as dihedral terms. And so that's the philosophy of ReaxFF, is that, okay, you give perhaps for rethermalization, you give up a little bit of accuracy that you get close to the equilibrium distance, but through this bond length bond order relationship that you zoom out, you can start breaking and forming bonds. So this is a proper Morse type behavior that you would expect for a carbon-carbon bond. In this case, CC stretching and reforming. On top of that, there's also a charge aggregation scheme. So you can look at the charge transfer between different atoms to start breaking and forming bonds. Now, since you have all bonded atoms, so the neighbors and the next nearest neighbors and the next nearest neighbors, so bonds, angles, and dihedrals, you need a description for that in terms of the expression of harmonic potential, if you will, as well as the bond length bond order relationship. You need the charge equilibration on top of that. You also need the other non-bonded terms, so you have the classical electrostatics as well as the van der Waals functions. You have all these terms going into your parameterization. So you need a lot of parameters to make this work. And it's a lot of hard effort to do that. It also makes the force field slightly less efficient than a harmonic force field, but still it would typically be roughly 1 million times as fast as typical DFT calculation. So to increase the number of atoms, that would be the cost for a ReaxFF calculation. In between, you would have DFTB at roughly 1,000 times as expensive as a ReaxFF calculation. And then there's this key calculation being a million times or 100,000 times as expensive as a ReaxFF calculation. It's formally linear scaling, and of course our DFT implementations are formally linear scaling as well, so they're MOPAC. If you have other approaches beyond DFT, then you get worse scaling than MQ, so you're particularly hard pressed to find any application to very large systems. Sorry, we're turning on the vacuum here at the back, so I hope it's not too noisy. Together with Arie van Duin, so Arie van Duin was a long-term postdoc in Bill Goddard's group at Paul Beck, and so Bill Goddard and Arie van Duin are still the two most well-respected experts in ReaxFF. With Arie, we worked together to take his private code, merge it into ADF, integrate it into the graphical interface, and speed it up a little, remove a few bugs, parallelize it, and we continue to work on that. The idea is that now, since it's integrated into all our codes, it's more usable for people, so you can more easily set up your systems. Ideally, you'd be able to analyze what goes on, so at the moment you can analyze all the different fragments, but we're working on techniques for event detection and so on. And you can much more easily sort of integrate it with all the other codes that we have. Just a few examples, you can look at materials and look at their degradation behavior. So there's an example, we're looking at silicon carbide. Silicon carbide reacting with oxygen or water. Your high pressure, high temperature calculations, and then you try to back out the rate constant. So in an Arrhenius type plot, try to back out the Arrhenius parameters, and you can then put it in a model that will allow you to predict the longer time scale behavior of these materials. So you can mesoscale or macro scale behavior of these types of materials. You start out at the atomistic level. That will give you, in this case, rate constants that then go on into the macroscopic models. Another example is where you want to have a look at how nanoparticles start aggregating in aqueous solution. So how do you form crystals from these nanoparticles? In this case, there's roughly 10,000 atoms in a simulation box that can be easily run on a desktop machine, so it's in a quad-core processor. You can run your simulations at slightly elevated temperatures to accelerate the dynamics. And you can then start to see how these nanoparticles find each other and they start growing in the right crystal structure direction. So here's an example of two of these nanoparticles finding each other. You can see at a certain stage during the simulation they start touching themselves, but they still have time to rotate and sort of find each other in the most optimum direction to start then growing in the 1 and 2 direction at MOPAC in this case. You can probably get away with doing these key calculations on some of these snapshots, but it doesn't give you the full picture of the dynamics, right? So it doesn't give you the picture that actually these particles, when they find each other, they do have time to sort of dance with each other and find the right direction for growing into the right crystal structure. Okay, in this case, the 1, 1, 2. Okay, so I mentioned there's a lot of parameters that go in there. That makes it also more difficult to apply to the system of the interest. So the sunny picture would be that of this periodic table here, everything that hasn't been grayed out at some stage in time has been treated with ReaxFF. So a large part of the periodic table has been covered. However, if you pick a random 3 or 4 elements, chances are that there's no force field available for those specific set of elements because we need all the different interactions for 1, 2, 1, 2, 3, and 1, 2, 3, 4 interactions. So within our distribution, last year we included 17 force fields covering 19 atom types in 2014, so it's released 2 weeks ago. It has roughly doubled, and the number of atom types that have been included has been increased by 50%. But still, what we want to give people is at least a tool that they can build their own force fields. So we do collaborate still with all the ReaxFF groups and the groups they're collaborating with, but we're also collaborating with groups that are good in global optimization problems. Right? So essentially, if you have a highly dimensional optimization problem, such as finding the right parameters for your system, you move to global optimization techniques. So that's genetic algorithms that's developed by Ben Hopkins and Q, or there's Anisotropic Monte Carlo, which is included in the current release. And if you're interested in that, I'm currently trying to organize a web demonstration by next week to demonstrate how that works. So just to give you an idea, the difference between hand optimization and global optimization techniques. So Anisotropic Monte Carlo simulated annealing, developed at the technical universities Eindhoven, applied to ReaxFF parameter optimization. This path search here on the top right. This is your error in your graph, and this is the iteration that we have. So the error is the difference between the DFT data that you typically use as a benchmark, but you can use any sort of data used as a reference, and the energies you get out of your new set of parameters. So this is still what ADF and DFTB does, hand by hand, optimizing each one of the parameters into the next parameter, hand optimizing them. Since he knows what he's doing, he's very good at that. It only takes him 2 weeks, he says. Typically, he's quite happy with the results. And as I said, he knows what he's doing, so he has a good feel of what the parameter should be. So here you can see that this particular example says magnesium sulfate hydride. This is the error you get when you do hand optimization. You see sometimes you stop, you go down, or you go down a lot. And after 1,000 iterations, this is the error with respect to the benchmark. The Anisotropic Monte Carlo approach, on the other hand, just randomly sort of samples different parameters and also memorizes what it has done, rather than Monte Carlo moves with an acceptance rate depending on the difference in penalty function, if you will. You see already in a few iterations you can get done, and you get a better force field than you would get by hand at this time. The ultimate force field is much better than the one you would get by hand. It's about 3 times less difference between the ReaxFF and the DFT data. So this all looks very promising, and it is, but there's one big warning that goes into that. So you can see for the training set, that's depicted here at the bottom, the DFT energies and the ReaxFF energies for a set of configurations are spot on. Right? So for the training set, there's very good agreement between the ReaxFF and the DFT data. But that's, of course, a well-selected set of data, just to show you how well you can do. There's other data that's less well inspired by ReaxFF. So you cannot dream to get a perfect force field that describes all of the DFT data to a perfect extent. So you need to think about what you do with your training set. So you need to think about which configurations are important that you want to put into your parameterization. But more importantly, if you then have a ReaxFF force field that you want to run your dynamics for, it could be that your sample areas of phase space that you didn't think about reaching in the ReaxFF parameters don't necessarily describe that very well. So you probably want to do this in a few iterations. So you build your DFT reference energies, you get your force field from this automated approach, you run your dynamics at a couple of thousand Kelvin, take a few snapshots, calculate the DFT energies for those, then re-optimize your force field and run the dynamics again, just to make sure that nothing silly happens, right? So most time, even if you do parameterization automatically, it goes into checking whether nothing stupid happens. Okay, so ReaxFF, we're working on further development of that as well. So one of the things that has been implemented is Grand Canonical Monte Carlo. I'll slide in that later on. What we're working on currently is acceleration techniques. So one of those is parallel replica dynamics. So you replicate your system in a number of different directions, and then the sample base that gives rise to reactive events. For that, we also need event detection, so we need to be able to see where things react or where they don't react. We also already have available is force bias Monte Carlo, so that's more or less related to method-dynamics or hyperdynamics, but rather than looking at the energies, you look at the forces, and we randomly pick up the system according to the forces. We're working with a number of groups worldwide to include other acceleration tools, and I think we want to couple each one of those so then you can actually run the dynamics at the millisecond time scale. And to improve usability, we also want to have a few analysis tools available, so we're building a platform basically that will allow you to much more easily analyze what's going on inside your trajectory. So this is Grand Canonical Monte Carlo. In a nutshell, what it is you basically do Grand Canonical sample the system under different temperature and pressure conditions. So let's say we've got a model nanoparticle here, palladium nanoparticle here, that under working conditions will have a certain oxygen and carbon pressure. You will see that you will actually start to make, in situ, you make a different catalyst. Right? So you get surface oxides, you also get oxides on the inside, and that will, of course, affect the catalytic properties of that one. So you can do Grand Canonical Monte Carlo to basically get your idealized in situ structure under given thermodynamic conditions, and on top of that, then you run your reactive molecular dynamics. Right? So you get the kinetics from this catalytic particle under operating conditions. That's described here. So that's from groups at Penn State, so Michael Rannick and Sensler. They're in a different department, but also in Penn State. Force bias Monte Carlo. I probably won't go in too much details, is probably because I don't understand it too much, and I'll try to give you the gist of it. So when you run method dynamics, when you're sitting inside, you're sampling an area, a closed space, where nothing much happens, that's typically happening at a minimum, you start building up Gaussians there to kick out your system traces of a phase space that have already been sampled. So you slowly start building up here potential energy. That will allow you to get the free energy of getting out from one basin to the other basin. That I understand relatively well. Then the force bias Monte Carlo is related to that approach, but rather than using a potential, you use the forces. And the force bias Monte Carlo basically allows you to go up against the forces to basically climb on top of one well, from one well climb on top of the transition state onto the other well. And that then allows you to accelerate the dynamics. There are a few questions that are related to actually translating that back to proper time dynamics, but those have been solved. To give an example of the difference between temperature accelerated dynamics and force bias Monte Carlo accelerated molecular dynamics. Here's an example where Knight, the University of Antwerp, has looked at carbon nanotube formation catalyzed by nickel nanoparticles. So if you start growing carbon nanotubes surrounding a nickel nanoparticle here, if you just ramp up the temperature, that's a gray curve here, and that corresponds to this picture, you get a grossly deformed carbon nanotube. Because the temperature is too high, the system essentially doesn't have any time to settle down into its ideal configuration. So this is a case where temperature accelerated dynamics doesn't work because the kinetics are different at high temperature than they are at low temperature. We need different acceleration techniques, and in this case, that's the black curve here. You can see you get much more smoothly formed nanotubes when we do the dynamics by this bias approach. Right, 2 slides then on COSMO-Rs, and then I'll try to shut up. So COSMO-Rs is a conductor-like screening model for realistic solvents. It's a quantum-based approach trying to assess thermodynamic properties of liquids. and that has been described by Andreas Klotz. It's been pre-parameterized in ADF, and that allows you to calculate
Ebony, open the door, please.
thermodynamic properties like vapor pressures. You can get really good agreement with the experiments, fission coefficients, so if the molecule is moving between two different solvent phases, hydration energies, so solvation energy in water, and there are a number of other properties that you can calculate as well. And the idea, since it's quantum-based, is that it goes beyond experimentalization as opposed to other methods that are parameterized like unit-method. In our COSMO-Rs implementation, we also have the segmented activity coefficient implementation by Singlet and the University of Delaware engineering. And we also have COSMO-X, which essentially it's called X, but it will be SEC-3D, which is based on this segmented activity coefficient, but it includes 3D information. So 3D information typically is not there because what we do in COSMO-Rs, in a nutshell, again, is basically you try to take into account all these interactions by looking at a 1D histogram of charges on the surface either inside a dielectric continuum. So the different number of steps that we do, and everything basically is done for you in ADF, so you don't need to think about it, but just to give you an idea of what goes on. If you're interested in properties of a molecule that's interacting with itself or other molecules in the liquid phase, if it's not already in a database, you calculate the molecule with a set prescript, and that will do geometry optimization in the gas phase, and then on top of that, they will do a COSMO calculation, a dielectric continuum going to infinity, so you have a perfect conductor surrounding the molecule. So this little picture here on the top right, you can think of that as thin foil representing the surface cavity, and on top of that, those little dots there, those are the surface charges that are calculated when you stick this tin foil inside of the perfect conductor. Right? So you have a dielectric continuum of infinity. And once you have those charges, you take a further approximation, you segment them, or you histogram them into a 1D profile, a signal profile. That's basically a summation of all the different surface charge areas. Once you've done that, then you can calculate the pairwise interactions of those molecules in solution of interest. And you can do all this physical thermodynamics you get from the activities that you calculate for these signal functions. Just a few examples. You can calculate solvation energies in water, calculate it versus experimental values, kilocalories per mole, so you can see typical accuracy is about 1 to 2 kilocalories per mole. Solubilities you can calculate if you know at least the heat of fusion used as an input parameter. You do the thermodynamics for the solid liquid equilibrium. It's not something that comes naturally from the COSMO-Rs theory, so you need the heat of fusion for it. Partition coefficients, so optimal water coefficient, partition coefficients that's related to how happy molecules are going either in the water phase or in the fatty phase, so that's related to lipophilicity. It's also related, for instance, to how molecules could go into different biotopes to ecological activity of certain properties. Accuracy is typically within 1 log unit for those type of operations. Calculate vapor-liquid equilibrium, so that's the vapor pressure of the ternary mixture. You can just about visualize that. There's different composition lines, and the color coding is corresponds to the vapor pressure. We can have more components into the mixture, no problem. I just have to try and visualize them. pK values, you can get much better prediction using COSMO-Rs, especially if you use external reference, so you know, for instance, the acidity of your external reference, and then calculate the pK values with respect to that. Yeah, so typically the accuracy you can predict is within 1 pK unit. But it can be worse, right? There's no guarantee that it always works. Okay, so I think Yeah, so there's development going on there, especially in the Singlet group and in collaboration with the three groups in the Netherlands, where you can get much better vapor-liquid equilibriums using this COSMO-Set model versus, you can even get better predictions than uniset in some cases. But it's ongoing development. This approach, the SET 2013 approach, is available in ADF 2014. Right, so just a one-slide summary. ADF modeling suite goes from ADF, where you can do large static calculations up to say 1,000 atoms at the full DFT level, or if you use a subsystem DFT approach or QMM, you can even treat entire proteins. So there's applications of frozen density embedding that have treated 11,000 atoms fully at the DFT level. We claim to be quite efficient and accurate, especially for spectroscopic properties. We have transition metals, heavy elements, and so on. Periodic DFT extension that has a number of unique properties related again to the state-of-the-art orbitals in combination with the relativistic Hamiltonian, as well as to the fact that you can include effects that are in the third dimension perpendicular to the representation. I'll explain a little bit about where we're going in terms of approximate quantum-based methods. So they're still quantum-based. DFTB actually is still a quantum method, and ReaxFF is benchmarked with respect to DFT data. All of those two methods at the moment arise in the usability related to not having any parameters for a system of your choice. So we're working very hard to make that more easier and more usable. For those systems where there are parameters available, of course, you can get pretty nice results for large systems already as it is. I touched briefly upon COSMO-Rs. So I think I'll stop here and I'll take any questions from either side. So from people not viewing from ANU, you can type in questions in the chat box. People at ANU, I hope I can hear you if you have any questions. Otherwise, you can use the chat function as well. Are there any questions at this stage?
No questions from ANU. You've covered a hell of a lot of material there. Thank you very much.
Okay, you're welcome. I see a question popping up at the same time. So there's a question popping up, I don't know if you can see it, about DFTB approaches for transition states. So there's a question whether DFTB is reliable for transition state structures. In principle, it should be applicable to transition states as well, because you take into account all the DFT data at different distances, so it goes into the parameterization. I must admit that I haven't seen much applications of DFTB to transition states, so I cannot say how good the accuracy is of DFTB with respect to DFT, of course. So DFT can also have its underlying problem for transition states. And since typically the DFTB data are parameterized against GJs, not hybrids, but you can parameterize them against hybrids, I would expect the DFTB might have the same problems as GJs for underestimating transition state values. So I hope that answers that question. So the answer is, the summary of the answer is, in principle, yes, but in practice, it might not be so good for these type of applications. That's the honest answer. Right, any more questions at this time and stage?
There was a SERS question a bit earlier that you might have missed.
So Rita, I didn't quite catch that. It's quite noisy here.
The chat box has a SERS question that I think you might have missed.
Yeah, I didn't see any question about that. So can you briefly recap the question?
Yeah, I'll type it up again.
Yeah.
I just want to read it out.
Sorry about that. You can, of course, always ask questions later on. I'll type in my email address.
It says it's impossible to do SEO
Oh, you've seen
on
that?
the whole surface. The whole surface is all made system. SEO surface enhanced.
Did it come up or not?
My question is, can we send him an email and ask him a question?
Yeah, I think he said that.
Okay, good.
Has he just cut off?
There's just give me his email address.
Alright.
Okay, so are you, Rika, are you trying to type up the question? Do you have any problems?
It's not coming up at the moment.
Ah,
I've lost my chat window.
okay.
So I tried to Skype one.
Yeah. Well, we can do that. I mean, I can close down the join me session and then we can have a brief Skype session, right, to take any Q&A from your side. Can we try that?
Just, let's how do I get this chat in here? Which one is it? From Skype?
Okay, so what I will do, guys, if there's no further questions at the moment, then as I said, I will upload the presentation. So I will also try to upload the video. And then you can look at that later on. I'll send you an email, but it will basically be on the page where you also registered for the web presentation. And there you can look at the slides, and then you can look at the presentation, and you can also send me any questions you have via email. If they're too technical, I'll just pass them on to support, but I will channel them into the right direction. So thank you everybody for listening in. I hope it has been useful for you guys. I apologize if there were any problems, especially in the beginning with the audio. It's just, yeah, I'm sitting here in a hotel, so I'm trying the best I can. Okay, so I see a question now. So is it possible to surface enhance Raman scattering on the whole surface?
Sorry.
Yeah, okay, so not in that approach. So that's a discrete approach where you have basically
Doctor, where's the money?
There you have the nanoparticle described with a polarizable force field with the discrete interaction model. We're working on a two-dimensional time-dependent functional theory implementation, or time-dependent functional density functional type binding implementation, and that will allow you to assess those type of problems. But it's not trivial to take into account the entire surface, because also what you need to do is when you have a slab, you need to take into account also sort of what goes on in the infinite direction in the minor z, if you will. So what I understand from the developers working on that, it's not trivial to actually set up two-dimensional time-dependent density functional theory for a proper surface. Yeah, it's slightly easier, but not trivial for a slab. But for proper surface description, at the moment, I think it's not possible to do that trivially. So for surface absorbate systems, to the surface enhanced Raman scattering, this is not possible at the moment. Okay, I'll wrap up now. So thank you once again for your attention. I'll send you an email with when the slides are available on the presentation. I'll close down the webinar. Again, if you do have any questions or problems, we'll chat with you guys in Australia via Skype for a bit. If you do have any questions, just email me. Okay, thank you.